Late afternoon session. Without further ado, I'll give you Alexandre on an approximate Shapley-Folkman theorem.
Okay, thank you very much. First, thank you very much to the organizers for the invitation. I'm happy to be back in the summer, especially since the summer falls this week, this year. And I'm going to talk about an approximate Shapley-Folkman theorem and mostly spend some time on Shapley-Folkman itself. And I should start by saying that this is joint work with Thomas Kerdreux and Igor Colin from ENS. Before I begin, just a very quick piece of advertisement. I'm recruiting postdocs, you know, shameless plug, at Ecole Normale for 1.5 years. This is basically the view from our office. This is what our office looks like, up to polylog terms. And so if you care about logs, then we can talk, but otherwise that's it. So feel free to contact me. But that's not the topic today. So today I want to discuss about minimizing finite sums. So very generic problems which look like this. So we assume a little bit of structure, but not too much. So we're going to minimize this sum of decoupled functions, sum of fi of xi. And the main assumption here is that the variables xi are completely decoupled. Okay? Of course, if they are coupled, you can add the coupling constraints in the add dummy variables and add the coupling constraints in the constraint set. Okay, so it's not a very strong assumption, but basically this is the structure we care about. And I'm sure most of you are familiar with at least some problems of this form. They are ubiquitous in machine learning and statistics. And there's been a recent stream of works on their computational complexity in particular, showing that because of this finite sum structure, you could expect better performance than for generic minimization problems. These results are focused on very particular instances of these problems in very particular regimes. They have certain memory requirements and so on, so they are not as generic as the structure I'm detailing here. But basically, what they show is that provided you have this finite sum minimization structure and a certain number of technical assumptions, you can expect much faster convergence than in the standard case for stochastic gradient, for example. Right? So that's computational complexity. But what I would like to discuss today is not really computational complexity, but robustness to non-convexity issues. And again, I'm sure you're familiar with problems of this form where non-convexity turns out actually not to be a problem. The simplest example of all is probably lasso, or problems such as SCAD or H0 minimization. I'm writing them in a slightly different format here so that they fit this decoupled finite sum minimization problem, but this just means introducing an extra variable. So the notation is a bit heavier, but these are the problems you're familiar with. Right? So penalized regression, empirical risk minimization, multitask learning, and so these are all classical statistical problems. Resource allocation, in particular the unit commitment problem, also has this format in economics. So the structural assumption that you're minimizing this finite sum is pretty meaningful in many fields, right? So just to summarize what we know about these in some particular cases, again, assuming this format, there is this stream of results I just mentioned on the performance of the stochastic gradient method for when you minimize finite sums, where you can show in some cases that you get linear convergence. Of course, this only holds in certain regimes. There are caveats about what you're supposed to store. It's sensitive to parameter choices, etc., etc. But the fundamental driver behind these improved complexity bounds is this finite sum structure, which is a surprise because when you say this, it seems you're not assuming much, and yet you get this very significant impact on computational complexity. Right? So that's a recent surprise, and there's an entire alphabet soup of methods taking advantage of this structure with efficient methods. They do behave well on paper, and surprisingly enough, they also behave well in practice. So this is an important message about finite sum minimization. But again, this is not the main focus today. What we're going to talk about mostly is the fact that because of this finite sum minimization structure, these problems tend to be more robust to non-convexity issues. And this, of course, has been heavily studied in the context of the lasso, for example. I should cite, of course, there's an infinite stream of references in this case, and I'm not going to cover it. But I should cite at least 2 results in this vein where, for example, the lasso-like recovery results were shown to hold for weakly convex penalties by authors such as Lowe and Wainwright or Chen and Gu, right? So basically, instead of putting L1 here as a penalty, you put a weakly convex penalty function, such as a SCAD, for example, and you get very similar performance than in the lasso case, both in terms of statistical performance and in terms of computational complexity. And of course, these results are very specific to the lasso and perhaps not as generic as what I'm claiming here, but we'll see that we can kind of suspect that the finite sum structure is perhaps enough to justify the fact that we're robust to non-convexity. And that's the idea we want to discuss today. Okay? But of course, the structural assumption was not born with empirical risk minimization, and people started to work on these problems for non-convex functions fi in problems concerning economies where consumers have, for example, non-convex preferences to show equilibrium in this context, or in classical production problems when they focus on unit commitment problems with non-convex cost. And in all these cases, we have results showing that the problem is more robust to non-convexity issues than you would expect, and they're all, as we will see, connected to one central underlying principle that I hope to illustrate today a little bit more in detail. Right? So just to fix ideas, today we're going to focus on this particular formulation of the finite sum minimization where the constraints are affine, but up to some caveats, everything I'm going to say generalizes to constraints of this type, nonlinear constraints. It gets a bit more complex, but there's no major obstacle to the analysis, so you can assume that basically this linearity assumption is fairly mild, right? Trust me on this. We can talk offline if you want, right? So there are references which cover this case, but I want to keep things light. And so today, at least, we're going to cover the linear case. So again, we have a separable objective function. We minimize the sum of functions fi over decoupled variables xi, so they're all independent. And we have this coupling constraint, which is linear, and all the coupling information in the problem is summed up in these linear constraints. And then we have additional block constraints on the independent variables xi. Right? That's the basic underlying format for today. And before I come back to this optimization problem, I'd like to sort of go back in time and discuss a fundamental result of convex analysis that seems bizarrely forgotten and will allow us to say a lot about non-convexity issues and finite sum minimization. And that result is called the Shapley-Folkman Theorem, and it's both, at least in my opinion, surprisingly effective and surprisingly simple to prove. So we are going to do both. So before I start, just a quick reminder, the Minkowski sum of two sets, x and y, is the set of vectors x plus y, where x is in x and y in y, right? So if you take two polytopes, for example, their Minkowski sum is a larger polytope. It looks like this, right? But this is workable for any sets. It's hard to compute, but we can do so graphically at least. And the main property we're going to care about on Minkowski sums today is the fact that if I take the convex hull of a sum of sets, this is also the sum of the convex hulls. So taking the convex hull and taking the Minkowski sum commute, right? And what's really interesting and intriguing about Minkowski sum is that it has a convexification or a convexifying effect. None of these words are in the dictionary, so who cares? But it makes things convex, okay? And so let's illustrate this graphically. If I take the L1 half ball, it's non-convex. And if I take the mean of two L1/2 balls, what I get is this set here. So this is the mean of two L1/2 balls. If I take 10 L1/2 balls, I get this. And if I take an infinite number of them, I get this, the L1 ball, right? And I can also do that with more bizarre sets. So it's an age-old tradition to do things with digits in machine learning when you run out of imagination. And so let's assume these are not digits but point sets, and let's take their Minkowski sum and see what it looks like. And when you do that, it's combinatorial. So I cheated and did it by sampling, but it's not a very expensive proposition, so you get a pretty good approximation of the result. And what this says here is that the sum is this. And this is not a very interesting set, but at least it's close to being convex, right? So these are admittedly arbitrary. There aren't too many of them. I'm taking the Minkowski sum of 5 sets. I divide by 5, and what I get is something that is very, very close to being convex, right? And so this phenomenon is actually surprisingly easy to analyze, and it's summed up in a result known as the Shapley-Folkman Theorem. The reference is to Star, but Star actually heard of the result through private communication with Shapley and Folkman, hence the difference in names. But what this result says is that if you have a list of sets, Vi, n of them, in dimension d, and you pick a point inside the convex hull of the Minkowski sum of these sets, then you can also write that point as the sum of n minus s elements in the original sets Vi and s elements in the convex hulls of the remaining sets Vi. Okay? And the important fact here is that you can actually bound the number of sets over which you take the convex hull by the dimension of the space D. Which means that if the number of terms n grows much faster than the dimension D, the size, the relative, and all your sets have roughly the same size, the size of this term here, which represents the difference between the convex hull and the original Minkowski sum of sets, becomes negligible. And the Minkowski sum is actually close to its convex hull. That's it. And the proof of that result takes one slide, so let's do it. So suppose X is inside the sum of convex hulls. By Carath eodory, we can write it in this format, right? And I'm writing things in a sort of block representation. So Z is X and a vector of ones, and Zij is a set of vectors Vij in the original sets Vi, and Euclidean basis vectors, so that I both enforce the constraints that the lambda sum to 1 for each set I, and the constraint that the Z is a representation of, a convex combination of the Zijs, a conic combination of the Zijs, right? So since Z is a conic combination of the Zij, I can invoke the conic Carath eodory theorem to write Z as another conic combination of the Zij with new weights mu ij, such that only n plus d coefficients mu ij are non-zero, right? I'm in dimension n plus d. I have a conic combination. Carath eodory tells me I can write another conic combination representing z with only n plus d non-zero coefficients. But now, because of the constraints, you have n sets, and you have to distribute n plus d non-zero coefficients mu among these n sets. And graphically, this looks like this, right? Because of the constraints, you need at least one non-zero coefficient per set. So this spans n coefficients in the representation. And then you add d coefficients on top of that. If n is much larger than d, in the worst case, you're going to have n minus d sets for which only one conic combination coefficient is non-zero. And if you have one conic combination coefficient non-zero actually equal to 1, it means you're actually in the original set, okay? So what this means is that the number of non-zero coefficients lambda ij in the conic combination representing your point z in the Minkowski sum, the number of non-zero coefficients lambda ij controls the distance to the convex hull. Every time you have a column here corresponding to a set with only one non-zero conic combination coefficient, the corresponding point is actually in the original set, the non-convex one, right? So if you have very few columns with more than one non-zero coefficient, you're going to be very, very close to the original Minkowski sum. And if they're all spread out and you have only one non-zero coefficient, you're going to be sort of, that's the worst case scenario, and you're going to be further apart. But that's it. You control the number of non-zero coefficients in that combination, and you make the Minkowski sum increasingly convex, right? That's the main message. It's 2 slides, but the second one was graphical, so it doesn't count. So consequences, if the sets Vi are uniformly bounded and with some bound R on their radius, then you can show that the Hausdorff distance between the Minkowski sum of these sets and their convex hull is bounded by R times the square root of the minimum and ND of ND, where this is the radius. And in particular, when D is fixed and N goes to infinity, if you normalize by N and you take the mean, this is going to converge to the convex hull of this mean of sets, okay, in the Hausdorff metric. There are versions of this result when N goes to infinity. This is known as Lyapunov theorem, and there are references here. There are also versions in Hilbert and Banach spaces, etc. This is completely out of scope today, but I'll refer you in particular to this reference if you want more details. You can write the same things for random compact sets, etc. But that's not the idea today. So this convexification phenomenon has important consequences in practice, and one of them is that it's going to allow us to produce a priori bounds on the duality gap of finite sum minimization problems where the functions involved are potentially non-convex. Okay? And so we start again from our generic, sort of generic finite sum minimization problem here. Again, we do not assume that the functions f are convex. We make other sort of simple technical assumptions to keep things relatively compact, but that's it. And so you have a non-convex problem, and if you work in optimization, the first reflex is to try to form a convex relaxation. One way to do that is to take the dual twice, and if you take the dual twice, what you get is this. This is a convex minimization problem, and it's written in terms of the convex envelope of the functions fi, roughly speaking. What's the convex envelope? Well, it's the biconjugate of the function f, so the conjugate of the conjugate. Its epigraph is the closure of the convex hull of the epigraph of f. A very classical, simple example is, for example, the L0, the indicator of 0, or 1 minus the indicator of 0, versus the L1 norm in dimension 1, okay? So this is L0 norm in dimension 1 between minus 1 and 1, and its convex envelope on the interval minus 1, 1 is the absolute value, right? Fundamental property of the convex envelope for us today is the fact that by construction, because of this property, the convex envelope and the function itself match at extreme points of the epigraph. Graphically, again, this is a very simple statement. It means that the convex envelope and the function itself match at these points, right? Extreme points of the epigraph. So if somehow your optimum solution falls on a point which lies which is an extreme point of the epigraph of your convex envelope, you know that the relaxation will be tight because the convex envelope of the function and the original function will match, right? So we're going to be looking for extreme points of the set of optimal solutions because we hope that this is where we find the tightest approximations to the original problem. Okay?
When you write the indicator of y of xi, this is the optimization one or the probability one?
It's the optimization one, but it's just a trick to get rid of yi. It's a non-event. So that's one way of forming a convex relaxation and a dual. There's also a graphical way of computing the dual of an optimization problem. And usually this is just an excuse to wave your hands and has mostly aesthetic appeal, but is not really useful. In this case, the graphical construction of the dual will be important. So how do you compute the dual graphically? Well, you form the epigraph of the problem, right? So it's a mixture of the objective and the constraints. So it's a set that looks like this here in dimension d plus 1 plus m, where x, r0, and r satisfy these inequalities. You can project it on the last coordinates. You get this set gr. And the dual basically maximizes an affine form on this set. Okay? The details are not too important. I'll come back to the main point very soon. What's important is that you can form the Lagrange dual function of the original non-convex problem graphically using the epigraph and maximizing an affine form on this epigraph. And that the dual you get in this way is the same dual than the one you get by computing the dual twice and getting a convex relaxation in this way. Okay? Not crucial here, but the crucial aspect of all we're doing here is that in this particular case, because the problem minimizes a finite sum of functions, the epigraph itself has a finite sum structure. And the epigraph of our problem is actually the Minkowski sum of the epigraphs of the subparts, the blocks, the functions fi, right? So the epigraph of my problem is a Minkowski sum of these block epigraphs, right? And if you remember a few ideas about optimization, you know that when this epigraph is itself convex, you have zero duality gap, to oversimplify massively. So all the keywords are there: convexity, Minkowski sum, epigraphs. You get the idea, right? So that's the graphical argument. Just to introduce one more quick definition, f star star, so the biconjugate or the convex envelope of f is the lower bound on the function f. It's the largest convex lower bound on the function f. So this quantity rho f, which measures the lack of convexity, is always positive, and it's, as the name indicates, a way to measure lack of convexity. And that's how we're going to bound the gap. And the main result, directly derived from Shapley-Folkman, which is due to Aubin and Ecole in the 70s, allows us to bound the duality gap of my original problem in terms of these lack of convexities for the functions fi and the problem parameters. And so, very quickly, this is the optimum value of the original non-convex finite sum minimization problem. This is the optimum value of the convex relaxation. Of course, it's lower, but we can sandwich the optimum of the original problem by the optimum of the convex relaxation plus this gap term, right, which is the sum of the non-convexities. That's not a big surprise, right? But what's very surprising here is that instead of having n on top, so n terms in this case, in which case the result is trivial, of course, just add the worst case differences between the relaxation and the original problem, you have m plus 1. And m here is the number of constraints in my original problem. So in particular, if I have very few coupling constraints in the original problem, the bound I get for the difference between the convex relaxation on the gap basically between the convex relaxation and the original problem, this bound is going to be very small relative to the size of the objective. Assuming, for example, that this grows with n, if the number of constraints is roughly constant, this will quickly become negligible compared to this part here. And the duality gap will go to 0. Okay? So what this result shows is that loosely coupled finite sum minimization problems have very, very low gap when n goes to infinity and the number of constraints remains bounded, right? And so that's really good news. But in fact, if you look at things carefully, you'll notice that this bound is actually also quite conservative and that we can improve it in many ways. And that's the point today. So the proof of this result is also one slide, so we'll do it too. The day is almost over, but I'm sure you still have a little bit of energy. So in a very quick sketch, the epigraph is a Minkowski sum of the block epigraphs. Okay, you can show, because the epigraph is actually, this is the closed convex hull of the epigraph, you can show that it's also the sum of the closed convex hulls. Klein-Millman tells you that this is actually also the sum of the convex hulls of the extreme points of the epigraphs Fi. And these extreme points are precisely the points where the relaxation is tight. And this is where you invoke Shapley-Folkman. You know that inside this sum, only S terms are actually equal to convex hulls. All the others belong to the set of extreme points. And now you can bound the size of this subset S by m+1, the number of constraints. And for all these points, the relaxation is tight, right? So the error you're making here compared to the original problem is 0. And the error you're making here compared to the original problem is bounded by rho of Fi. And this is how you get the result. Okay? That's it. So this gives you an a priori bound on the duality gap based on completely tractable quantities. It's typically fine to compute rho. We have typically good approximations for an upper bound on rho. And of course, the gap bound becomes vanishingly small if n goes to infinity and the number of constraints is fixed and rho is uniformly bounded. The key issue here is that this bound is still conservative, and in particular it's written in terms of unstable quantities. We're counting, and counting is always bad. Okay? So it's written in terms of dimension, number of constraints, etc. And the question is, can we significantly tighten the gap bound using stable quantities, something else? And I'll give a few clues in what follows. So the first sort of slightly obvious thing to do is to say, well, I only have a very limited budget of non-zero conic combination coefficients to distribute in Shapley-Folkman. D of them spread among n sets, right? So in the worst case, to get the bound, you put only one non-zero coefficient per set, and you have D sets for which you're taking the convex hull. But you're not taking a generic convex hull in this case, you're taking a convex hull with only two non-zero coefficients. And that means that the rho k bound, lack of convexity bound we defined earlier is way too generic. Okay, you can define something like rho k, which is the convexity, the lack of convexity you measure compared to convex combinations with only k non-zero coefficients, and that can be significantly smaller, right? So if you properly account for the number of non-zero coefficients in the conic combination, you can already write your bound with much better, much more refined quantities that are also somewhat tractable. So that's one way to gain, to tighten the bound. The second is a bit more combinatorial in nature. So everything, the quality of the bound essentially depends on the number of coupling constraints, right? So the number of constraints in AX is smaller than B, the size of this linear system, right? So M. And if you think about it for a minute, this is a polytope, and this polytope does not have a unique representation. There are plenty of ways of writing polytopes. Some will be more economical than others. So we don't have to use this set of equations to represent the coupling constraints. And there may be a much cheaper way of writing these coupling constraints, one that involves much fewer constraints. And if we have much fewer constraints, we're going to get much tighter bounds on the duality gap, right? So can we get better bounds using shorter representations of P? Well, this is a classical topic, and it has to do with extended formulations. So what's an extended formulations? Well, we start from the polytope representing coupling constraints, and typically we're going to write it as the projection on the first coordinates of another potentially simpler polytope in a higher dimensional space. So you lift your polytope and you project the first few coordinates of your polytope, and in many cases, you're going to be able to find a higher dimensional polytope, which a much shorter representation that will allow you to considerably reduce the number of inequalities required to specify your polytope. And if you have fewer inequalities, you're going to get a tighter bound, right? So this procedure is called writing an extended formulation of a polytope, and the shortest extended formulation, the size of the shortest extended formulation of a polytope is called the extension complexity. And my claim is that you're already very familiar with these techniques because you're using it all the time. And the simplest example of this is the L1 ball, right? In dimension n, the L1 ball has 2 to the power n inequalities. And yet we routinely solve L1 minimization problems in practice. And the reason why we can do that is, among other things, because there is a very nice and simple extended formulation for the L1 ball. You lift it to a space of dimension 2n. You introduce 2n inequalities plus 1 equality constraints, and you have another representation of the L1 ball. And this one is much, much cheaper. It goes from exponential in size in dimension n to linear in size in dimension 2n, right? Very simple extended formulation. There are much more complex results. For example, on the permutahedron, which has 2 to the power n also facet-defining inequalities. There is an extended formulation in dimension n square using n square inequalities. And there's a recent optimal result by Goomans, for example, in 2014 that has only n log n variables and constraints. So again, what you see in the coupling constraints is not what you get. You can work on the representation of your coupling constraints to make them cheaper and to reduce their number while remaining equivalent to the original problem, and that will have an impact on the complexity bounds. There's a beautiful result by Yanakakis showing you sort of explicitly how to produce these extended formulations. They are directly connected to non-negative matrix factorization. It's a bit out of scope today, but it's so spectacular that I can't resist. So how do you compute an extended formulation? Well, you write S, the slack matrix of the polytope P. So you start by enumerating the vertices. This is where it doesn't really get practical. And you form this matrix Sij, which is essentially the slack matrix for constraint I at vertex j. So it's a very, very large non-negative matrix. And this sort of foundational result by Yanakakis in the 90s shows that this representation here is an extended formulation of the original polytope P if and only if S can be factored as the product of Fv, where F and V are non-negative matrices. So if you compute a non-negative matrix factorization of the slack matrix, you get an extended formulation, and the lowest rank non-negative matrix factorization gives you the shortest extended formulation of your original coupling polytope, right? There are stable versions producing approximate extended formulations using very similar arguments, but there's one key caveat in our case, and I won't go into too many details here, is that in the extended formulation framework, you're allowed to factor out equality constraints. In our case, we have to account for them, and so we need to count extended extension complexity a little bit differently. This can be done, but it's another exercise, and I won't go into detail. But what this means overall is that in the gap bound, we just detailed from Eklund and co-authors, we can replace M, the number of inequality or coupling constraints, by the extension complexity or the modified extension complexity of the coupling polytope. And that can be significantly lower by going from exponential to linear, for example. Okay, so lifting works, and here lifting means tightening the bound. It's very abstract, but at least there is a lot to be gained here in many cases. Udell and Boyd also showed that we can replace the number of constraints by the number of active constraints. So again, it's not the number of constraints in your coupling constraints that counts here. It's the number of constraints that are active at the optimum. And again, this number can be significantly lower. It's bounded by the dimension using Helly's theorem, but usually it can be lower. And the proof is slightly different. It uses a dimension argument I won't go into detail, but it's not really the same procedure as before. But again, it allows you to replace m by the number of active constraints, which can be below and give you better bounds. And one last lever you can pull on this bound is the fact that so far we've only used exact representations, conic representations of the optimum solution Z in the epigraph, right? If you want to produce a relaxation, you're going to get a little bit of error. You might as well give up a little bit of approximation error in your conic representation in order to get a much sparser representation of your optimum solution, since the number of non-zero coefficients in the conic representation controls the duality gap. So you're going to trade off approximation error in the conic Carath-eodory result with your duality gap bound. You're going to get an approximate solution with fewer conic combinations, coefficients, and at the same time, so you're going to incur a little bit of error, but at the same time, you're going to reduce the number of non-zero coefficients and reduce your duality gap bound. If you trade off optimally between the two, you get a better bound. Yes?
Just curious, so this point you are making, is it related to using, let's say, Maurey's method, Maurey's approximation?
Yes, that's exactly where I'm going now. Yeah, sure. So instead of using Carath-eodory, we're going to use approximate Carath-eodory, right? Except there's one caveat here. We're in a strange regime. Remember that this is only useful when the number of terms in the finite sum is n, is large, and the number of constraints m remains relatively small, right? So originally you have n plus m coefficients, and typically you want to go to a representation where you have about n coefficients, and m is small. So this is a version of an approximate Carath-eodory where you have a very high sampling ratio. You're going to keep sort of 95 or 99% of your coefficients. And the classical proofs don't work if you use, so there are two approaches to prove Maurey's result. One is using Frank-Wolf or mirror descent, and the other one is to use a randomization argument. And the key to getting bounds in the case where you have a high sampling ratio is to use results on concentration without replacement. That's the only idea. And if you do that, you get something like this. And essentially, the number you trade off approximation error here, epsilon, and the sampling ratio of your initial coefficients, right? And so this is a sort of, the original results are due to Serfling. The idea here is to write them in a sort of general Banach space because the vectors we care about have a block structure, and so we need to use slightly more sophisticated norms. So that's why we need a slightly more generic result. But otherwise, the proof is very similar to the classical results in this vein, using martingale arguments for sampling without replacement, as in these references, or in particular this one and this one, right? So that's a sort of Hoeffding Serfling bound, producing a high sampling ratio version of the approximate Carath-eodory theorem, and it gives you a better bound. It's still very conservative, but at least it shows you that you can trade off things optimally. You can write also a Bennett-Serfling version of this inequality to get rid of these diameter quantities that are very conservative, and that allows you to write explicitly the trade-off between reducing your duality gap by reducing the number of non-zero coefficients in the conic formulation and incurring this approximation error. Yes?
Sorry, the last slide was fine. But just as an example, if I have, x1 through xn, and I want them all to be equal. So I want x1 equals x2 equals x3 equals x4.
Yeah, so in that case, sampling will work beautifully.
So
no, this is bad, and what you want is this one because it depends on the variance. Yours will have zero variance, and you're going to get perfect approximation error. This one won't. Okay. Right. So that's the reason why you want Bennett-Serfling instead of Hoeffding. But in both cases, unfortunately, you don't put a lot of structural information in. You don't get much out. Your sampling ratios are still very, very conservative compared to what you would expect by running actually for example, Frank-Wolf to get an explicit numerical solution to the sparse approximation problem. So we still get very conservative bounds, but at least they cover the case you just mentioned. But don't go much further than this, please. So just to sum up, what we get is a priori bounds on what we get, what basically applying Shapley-Folkman to this problem structure produces is a priori gap bounds, tractable a priori gap bounds on finite sum minimization problems of this type. And the bounds are written in this format, and the key point, of course, is that they depend on the number of coupling constraints, and not on the dimension here. But even those bounds, even with this reduced limit here, are very, very conservative. All these terms are conservative. The bound on lack of convexity itself is conservative because of this argument counting non-zero coefficients. If we work a little bit on the coupling constraints, we can significantly reduce them by using extended formulations in some cases. We can replace M, the number of constraints, by the number of active constraints, which can be lower too. And we can use approximate Carath eodory to trade off a little bit of approximation error with a much reduced number of coefficients, and again, a better duality gap bound. All of this is very abstract. This is still work in progress. I don't have a very long list of nice, catchy, concrete examples, but the idea here is to illustrate the fact that, again, because of this finite sum format, and because of this regime where the number of samples we get, which is typical in statistics, is very large, you can expect finite sum minimization problems to be much more robust to non-convexity. And this is illustrated by the many components of this bound, which can be often bounded very explicitly, very efficiently. Okay, so to summarize, we get a priori bounds on the gap. They are good but conservative. And again, this is not very concrete, but the list of problems that are potential applications is fairly long, and hopefully soon we'll have more concrete examples to illustrate this. And to conclude, most of the papers which discuss the Shapley-Folkman theorem end up with the conclusion that it's very sad that Shapley-Folkman is not more used and more well-known in both statistics and optimization, and so I should probably end my talk by saying that it's a shame that you know, the Shapley-Folkman result doesn't get more publicity. Thank you very much. Yes.
So, can you say anything about stationary points or something like this? Because of course, I mean, if I looked at your sets, right, they've got all sorts of kinks and things like this, and so here, I mean, a priori, you know, I could have stationary points all over the place, and it seems maybe hard to actually get a solution to that.
So there are a few concrete things you can say, and one of them is directly connected to what Udell and Boyd say, which is that you should go through a purification step, right, like a 3-minute shower. So basically, if you solve the convex relaxation, especially using an interior point solver, you get a point inside the set of solutions. What Shapley-Folkman tells you is that because you want extreme points on those epigraphs, you're much better off looking for an optimum solution as on the extreme points of the optimum set.
Oh, I'm sorry, I think maybe my question didn't make sense.
Okay.
So if I just, you know, run some method on the sum of the FIs,
yes,
right, whatever it is, you know, I'm going to converge to a stationary point or a second order stationary
Ah,
point.
no, yeah, okay, okay.
It's not clear to me that I can say anything.
No, but this, at least, the message here is not about what happens when you minimize the original problem. It tells you what to do when you minimize the convex relaxation and you want to be as close as possible to the original problem. And it's going to give you a priori bounds on the gap between the two. But one way...
Is there any hope that you could, I don't know, say something about like stationary points of the finite sum or smooth stationary points of it because it's close to convex in some weird way, or I don't know what exactly.
It's not close to convex in particular on most points of the space. It's going to be close to the original problem at extreme points. So these are not uniform bounds, they're on a case-by-case basis. So you write these conic combinations on a case-by-case basis. It's not an explicit fixed decomposition. So the conservative answer is no, but it's a conservative answer.
So I have just the first one to clarify the message. So the obvious bound would be the row of the sum, and you replace it by the sum of the rows.
Yes, yes,
okay.
yes, yes.
And the argument is that it's easier to control the individual rows rather than the row of the sum.
No, the naive bound is the sum of the rows, but Shapley-Folkman tells you that you don't need the sum of n rows, you need only m of them, where m is the number of constraints.
Okay, so then if I want to look at a specific example, for example, LP penalized least squares where p is less than 1.
I've tried, and
Okay.
I wish it were at the end of the talk, but it isn't yet.
The number of constraints, I mean, here you end up having a number of constraints, which is essentially the number of terms in your sum, right?
Yes, yes, yes. If you do it naively, that's why you have all these results about melting down all these components. I'm hoping that by, for example, looking only at active constraints, looking at clever representations of the sections of the L1 ball, etc., you can melt the number of constraints to something that looks like the bounds you get for weakly convex penalties. But I'm not there yet.
Let's thank him, and the speaker is